What, you want me to do a song and dance? That ain't gonna happen. You be quiet. You got a problem, leave. There's the door. Door? Door? All right, some of you know me, some of you do not. If you do not, that's a good thing. If you do, I apologize. My name is Mr. Gilmore. I teach science and mathematics here at Clarkson High School. I am a physics teacher by trade, but currently I am teaching mathematics. So, last year, you might see some of my lecture, depending on how far we get through here. So, Mr. Eisele asked about 6-7 months ago, would you like to redo it? And I said, sure. And then throwing some things around, conformity, non-conformity. Let's talk about time. What is time? All right, this is where you have an audience participation portion. And this is where you jump in. All right, see, this is lecturer type of guy here. Audience participation. Don't be a stranger. Oh, look, 2017 state championship. Very good. What is time?
Time is a human concept of how much something has passed. It's kind of broad, stretching in that sense, in that we don't necessarily know as well. Not everyone knows as well as maybe they should, or maybe it's just a human construct that is sort of useful.
Yes, I agree. It's a human concept, but not really. Because within the physics world, everything will actually end up in heat. Heat causes chaos, and it's called entropy, okay? So entropy, as time moves on, there is more entropy, which is heat within the universe. So they can say, okay, time passes because there's more entropy in the universe. Does that make sense? A little bit, all right? Because everything that you do causes heat. Every time you drive a car, heat is released into the universe. That causes chaos. How do I know it causes chaos? Go ahead, young lady. Awesome. What happens to molecules when you heat them up? Go ahead, sir.
Move faster.
Oh, more chaos. They're moving faster, right? You take heat away, what happens? Slow down. More. Not chaos. What's the opposite of chaos? Come on. A little louder. Anybody? Order. More order, right? So how do we label time? Well, it's a sensing atom. I don't remember how many vibrations of a sensing atom that we actually have, but who cares? So many vibrations of an atom is 1 second, okay? Everybody knows, hopefully, 60 seconds within a minute, 3,600 seconds within an hour. Right? So let's talk about that. Light, we're going to go into Einstein's theory of relativity, talking about time dilation and how it actually happens. Because 1 second here on Earth is not 1 second somewhere else. It could be longer, or it could be shorter. Quit smiling, okay? Don't smile at the lecturer. It's creepy. All right. Oh, but I'm on tape. Sorry. All right. Some of these are my students. So, all right. So, concept is this. If you were in my class yesterday, you might hear a little bit. We're going to get more in depth into it. All right. Speed of light travels at 2.98 times 10 to the 8 meters per second. Nothing can travel faster than the speed of light. That's a theory. Has it ever been proven? Go ahead. No, because it's a theory. When you talk about laws, what are laws? They're proven to be a fact. Okay, so it's a theory. The theory has never been broken. All right. So, let's go. Where's my little clipper? All right. Time, that's what we're talking about. All right. Special relativity. You're in a spacecraft, right? And what's going to happen, ladies and gentlemen, you're going to shoot a beam of light up, and then it's going to hit it here, and it's going to go back down. Let's call this 1 second. 1 second to go up, 1 second to go down. It's a pretty big spaceship, right? But work with me. So how many seconds does this young lady on the little spacecraft see? If it takes 1 second for the light to go up and 1 second for the light to go down, how many seconds is that? 2 seconds. You guys agree with that, right? Good concept. Now, as this spaceship is actually rocking through space, or moving very fast through space, if you have an observer on Earth, does the observer see the same thing? And the answer is maybe. I don't know. Let's find out. This next slide. No. Because take a look. I brought my prop. All right. If I stand here relative to you, right, the ball goes up and down. You guys agree with that, right? I am not moving. Now, do not watch me, because I don't know if this is going to work that well, because I'm not good at catching. If I'm walking and I throw the ball up and it comes down, what did you see the ball do? Go in an arc. What did I see the ball do? Just go straight up and down, because I'm moving at the same rate as the ball. Do you agree with that? Same concept, okay? The guy on Earth who's old and wants to be on a spaceship, the light goes on an angle and then comes back down. Now, if it takes 1 second to go up and down, how many seconds does it take to go on an angle? Think about it logically. Take your geometry classes. Who's in geometry or algebra 2? Talk to me. That length. The hypotenuse is always the longest side of a triangle.
Yeah, that's it.
So, if this is 1 up, right, and let's call this 1 over, okay, for the sake of it, 1 second up and down, 1 second over, that length is what? Is it 1 second? No, it's what? It has to be more than 1 second. Okay? So the person on Earth that is observing this happen, it's all relative to where you're at, right? The time that he sees is more than that. More than, okay, it's 2 seconds. More than 2 seconds. You guys are great. Because it takes 1 second for it to go up and down. If I'm not moving, you see the ball go up and down. 1 second up, 1 second down. Start moving the speed of light. What happens? It takes 1 second to go up and down, but now this is the length of the hypotenuse of the triangle. It's more than 1 second, or more than 2 seconds, whatever I'm using. You guys agree with that statement? Kind of? Right? Okay. So relative to the man on Earth, more than 1 second has passed. Relative to the lady in the spaceship, right, only 1 second has passed. More than 1 second? 1 second, or whatever, I'm saying. It's called time dilation. We think of 1 second as so many vibrations of this atom. But it all depends how fast you are moving relative to the speed of light. You get that funny face. Does that kind of make sense? A little bit? All right. Now, that's the equation. Ooh, big stuff. It's nothing. You know, it really isn't. Okay? T is the resting time, or the person that's not moving. We're going to usually use 1 second. Okay? Velocity is the speed of the spacecraft in which it's moving. The c is the speed of light, 2.98 times 10 to the 8. This is the equation that Einstein came up with. And t prime is the change in time relative to each other. Kind of makes sense? I'll go to the next slide. Okay. So, time dilation. So if I'm standing above our solar system, Mr. Golden Sun, the planet's moving around, right? If I'm standing up here not moving, okay? Venus has a time dilation of 1.000000009 seconds. So 1 second on Venus is 1.0000009 seconds to me. Earth, 1.00005, right? Not that much time difference. Why? Because Venus is only moving at 38,000 meters per second around the sun. Relative to the speed of light, it's very fractional. Okay? Earth is only moving at 30,000 meters per second around the sun. Not much difference there in time. Satellites that orbit the global positioning satellites that orbit the Earth, there's 24 of them. Their time dilation is less than this because they're only moving about 3,000 meters per second around the Earth. But they still have to take that in consideration, especially for global positioning satellites. Okay. So 1 second to us, right, is different than them. It's less than 1 second. So in order to get a good GPS system, they have to take that into consideration. Questions, comments, or concerns? Oh, tough crowd here. All right.
They get it.
Do they get it? Let me ask them some questions. All right. Next. So, what are the fastest things that travel through space? Things with mass. Okay? Well, some of these supernovas, as they blow up, they'll actually push protons close to 99.9% of the speed of light. So they are moving 99% of the speed of light. Well, what's the time dilation there? Hopefully that's my next slide. So these supernovas, right? They put out particles at 2.967-94080 meters per second. Their time dilation is 7.088 seconds. What does that mean? Well, if we could actually shrink ourselves down to the size of a proton, go that speed, 1 second can pass for us, and relative to the rest of us on Earth, how many have passed? 8. That's what it means, guys. As you approach faster and faster the speed of light, what happens to the time for you? Nothing. You're on this little proton. You're approaching the speed of light. 1 second passes, 1 second passes. You're okay. But what about everything around you? Time speeds up relative to you. So if we can get a video camera and actually tape this lecture, you would be looking at that lecture moving 8 times the speed. What would I be doing? Then we would leave. One day where you is actually 8 days for everybody else. Does that make sense? So when you, go ahead.
So the time dilation is always compared to people on Earth? Like, so, okay, so like 7 seconds on Earth would be 1 second for the protons?
Yes.
Okay, so it's always just compared to Earth?
No. It's
No.
anything that's stable.
Okay.
Because if you're not moving relative to the speed of light, right, then yeah. But if you're moving, because it changes, because if you're moving at 0.99% of the speed of light and someone behind you is moving at 0.98, there is not that 8-second delay, probably less than that, and way less than that. Because that person is also moving that fast. So it's all relative to where you're at. Yeah, what? Go ahead.
So if someone were standing on top of that proton and someone on Earth would that, since you're moving faster, would that ever like affect the chance?
No, it will not affect you because you're on the proton. But the people that are on Earth, oh yeah, they're getting older 8 times as fast. Relative to you. Relative to them, It's just normal, you know? Well, here's the part I want you to think about. What happens when you hit the speed of light? Go ahead.
Well, what happens in a black hole when there is no light?
Well, there is light.
Okay, so how?
Light, because the black holes are so massive that the gravitational attraction of the black holes pull the light in. Now it begs the question, because gravity only works on, we're going off topic, but I like it. Begs the question, we think light is an electromagnetic wave, right? It has no mass, but gravity only affects things with mass. But if light cannot escape, what is light?
I don't know.
Hold on, it gets better. They actually think that physicists are working on or thinking that if you take all the light and compact it, you'll actually get mass. Because we can actually take matter and turn it into energy, right? That's what the sun does. Through its,
So is this all theory or is this proven?
oh no, this is theory which has been tried, disproven, and it has not been disproven. You understand? You cannot go at the speed of light. Okay? So to say that, is it proven? I'm going to say it cannot be proven, but it's a theory that's been challenged so many times it's never been disproven. And reality is, it's kind of been proven because once we start putting the geosynchronous, once we start putting the satellites in space, they found out that the clocks were not the same. So they know that something's up. You know what I mean? So the question is, as you approach the speed of light, okay, what happens to time relative to somewhere else? What happens to your time, right? And what happens to time to the people who are on Earth? As you get closer and closer. Because when you hit the speed of light, goofy things happen. Because if you take a look at that equation, which I got rid of, you cannot divide by 0. Right? So what happens to time? What do you think? This is where part where you guys talk for a second, come up with a good question, good answer, and I'm going to drink the coffee for a little bit. All right. Quit smiling. Put your legs down. Sit up straight.
Wait, can you repeat the question?
If you could actually go the speed of light, what do you think actually would happen to the rest of the people on Earth, and what would happen to you from a time standpoint?
Everybody would be dead. Well, it can't be divided by 0.
And we're done? What would you see if you had a camera that looked back on Earth? What would it look like?
That's what you're saying? Is everything
I was on Earth looking at the guy on the spaceship. What would the spaceship guy look like? And if I was a spaceship guy looking at the people on Earth, what would the Earth people look like?
I'm just like,
Oh, you can't. It's all theoretical. You can't do that because radio waves travel speed. I know what
That is.
Got something? Huh? Go ahead.
So, say we can't be divided by 6. Just time not. Or like, I don't know, because you don't know because it can't be divided by 0 and you're going so fast. Like, of course, like, I don't know about the people around you, but you know people would age astoundingly quicker.
All right. Lie down, please. Pull it together. Pull it together. All right. Go ahead.
Oh, well, since it can't be divided by 0, I just kind of inferred that time would no longer be a concept.
If you're on Earth looking at the person on the spacecraft, what would the person on the spacecraft be doing? Motionless. If I was on the spaceship looking at the people on Earth, what would these guys be doing? Moving so fast you can't even see them. Right? So if you're on Earth, looking at the spacecraft, time would have stopped for that guy. You would see him, 1 second would still pass relative to him. Okay? But relative to the people on Earth, right? Time would have stopped. He would be motionless. Relative to the guy in the spaceship, 1 second is 1 second, right? Depends what's that. But if you could look at the people on Earth, you would watch time fly by. Go ahead.
What do human existence, when the person on the spaceship see human existence like end in
Maybe.
itself?
All depends. How long he's on there. Oh, yeah. Kind of creepy, isn't it? So think about a light wave travels the speed of light, right? What is that time to them? To the light wave? Because the only thing that travels the speed of light is the speed of light in space. So what is time to a speed of light? Or a light wave, electromagnetic radiation? Go ahead, sir.
What if the time dilation value was less than 0?
Sorry, one more time?
What if the time dilation was...
You cannot. If it was less than 0, then you go faster than the speed of light. And as of right now, the theory holds that nothing will go faster than the speed of light.
I just heard that when I was in New York at the TED, there was a physicist that said there's like a theory that seems like mathematically it's working out, that there's sections of space that are expanding faster than the speed of light. It's the only thing they've been able to conceptually fathom, because space isn't subject to the constrictions of like time and light, how we are speed. You know, like space can do whatever it wants.
Well,
right?
there's an issue with that. If at the edges of space, what's on the outside of edges of space? Because during the Big Bang theory or inflation era, space and time were created all at once. So if you're at the edge, what's past that? You know what I mean? And if you're sitting there at the edge of space, looking back, what are you doing? You're actually looking back at the beginning of time. So, go ahead, sir.
If you take 2 points of light and then having like crossing and then having to go like that really fast, would the point where the lights where the beams of light intersect be able to go faster than the speed of light?
No, nothing can go faster than the speed of light. So, the concept, good question. Because if I'm traveling in a car that's going 55 miles an hour and I take my little squishy stress ball and I throw it, and I can't throw that fast, say it's 30 miles an hour, right? How fast does the ball go relative to a person on Earth? Well, it's 80. You guys agree with that? If you're traveling in a car doing 55 miles an hour, right? Because the ball is traveling 55 miles an hour. I can throw it forward at 30 miles an hour. So when it hits you, how fast is that ball going to hit you? Or a tomato or whatever. 80 miles an hour. Does that make sense? So if I have a flashlight, okay, and I'm traveling the speed of light, or really close to it, I can hit my flashlight, and I can watch that thing slowly but surely move out. Does that make sense? And if I can go, if I'm in my little, and it gets out about 10 meters out, and I hit my spacecraft to go the speed of light, that light beam will only be 10 meters in front of me all the way, because nothing can go faster than the speed of light. Does not matter what reference frame that you are in. All right. All right. So this discussion here is time. All right. Does it conform? Yeah, it conforms to where we're at. Does it not conform? No, not really, depending on what your reference frame is. All right. Get you guys thinking about that. Let me get my little clicker. This is actually kind of cool. All right, you're gonna like this part, because time dilation, we have something else going on. You're gonna follow my math here, maybe. All right. Full star, about Alpha Centauri is about 4.3 light years away. Relative to who?
Us.
Yeah, relative to us. Right? Now, if you can go 0.95 times the speed of light, or 95% the speed of light, somehow, right? that, it would take you 4.5 light years to get there if you were an observer from Earth. But if you were on that spacecraft, it would only take you 1.4 years to go. Why? Because you have a time dilation. We think because we're not moving fast as the speed of light, right? Time moves faster for us relative to the person on the spacecraft. So to him, it would only take him 1.4 years because of the time dilation. Now, we all know that length is distance times time. So if you're on the craft, going 0.9 times the speed of light times 1.4 years, that galaxy or that star is not 4.3 light years away. It's only 1.3 light years away. Cricket, cricket, cricket. Yeah. So besides length, we think that, okay, remember a light year is a distance of length. It's the distance that light travels in a year. Right? Awesome. So now, besides a time dilation, we have a length constriction. Length actually gets shorter between objects as you travel the speed of light. Okay, awesome. Think about that one. All right? Now, that was my science one. How do I get my math one? All right. While he's getting this set up.
We wrestle with the theory of knowledge, whether or not, when I open the unit, talk about mathematics, is it invented or discovered?
Oh, yeah.
And we talk a lot about concepts like that, where these things exist regardless of we observe them or not.
Yep.
That mathematics is just a description of things that already exist, even if it's theoretical. Just like a star exists without you seeing it, ideas exist without you giving it a label, right? So we really wrestle with mathematics being, and because science is, right, just
Yeah, it's
discovery,
applied math.
right, yeah, and so math working hand in hand with it usually goes along the same philosophical line.
Math is discovered. It is out there. We just have to have the brain power to find it. And as these brilliant brains go out, and not me, okay, I'm going to tell you that much. All right? Go out and think at this high level, they can actually do the math. Math proves everything. Okay? So, yeah, this happens, or blah, blah, blah. It's like, well, prove it mathematically. And the math is the key to everything. Well, watch out. So when you sit there in your math class, say, what do I need this for? Everything. Okay? All right. Go back to the beginning of time. No, not the beginning of time, after that. I need someone to count for me in Roman numerals. Go ahead. Roman numerals. Sorry, what did you say? 1, 2, 3, 4, 5, yada, 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 right? What am I missing? I, which is 1, I, which is 2, I, which is 3, I, V. Hold on. What am I missing? But there was no concepts of zero until about 300 BC or AD. I apologize for that. I don't have the exact numbers, but later as math moved on, the concept of zero did not exist. Okay? So I asked you to go in there and count the cows in the pen, right? You go, if there was nothing there, there are no cows. There was no zero. Okay? So zero finally came along. So if we start off, and I'm going to make this kind of quick because I did the other one. I actually like this lecture. It's actually kind of cool. Start off with natural numbers, which is your count numbers, right? 1, 2, 3, 4, 5, yada, yada, yada. Then the concept of zero came in. Zero. All right? Zero doesn't conform to the counting numbers, so what do we have to do? What do we have to do if zero doesn't conform? Make it conform, right? So what do? We dropped in the whole numbers. Your whole numbers are your 0, 1, 2, 3, 4, 5, 6, 7. Then the concept of what? Why are you eating in my class and didn't bring me any? Whatever,
my lunch
all right?
hour.
So after the concept of zero came in, and everybody accepted that, what was the next concept they had to wrestle with?
Negative numbers.
Negatives. I got -2 chickens. Think about it logically. How can you have -2 chickens? Go ahead.
You owe someone chicken.
That's what we accept now. But what about then? All right. So negatives were the next one, right? So that covers your integers. Then we're talking about rationals. Okay, life is good. We got the negatives covered. We got the zero. We got the positive integers covered. All right. Then what's the next set? They had to rationalize. Fractions. A half a cow. Think about what I'm saying. A half a cow. Half a cow. No, it's a cow or you don't have a cow. There's no half a cow, right? You know, the cow comes in on 2 feet, and it ain't gonna happen. But as time went on, rationals were in there. Rationals are any numbers expressed as a fraction, if you did not know. All right. So as the numbering system got larger and larger, we discovered things that existed that we did not know existed before. These are all your sets of numbers. Complex numbers encompasses everything. The real numbers, imaginary numbers, right? Rational numbers. Okay. Awesome. Questions? That's how math compensates, because if it does work, then we got to make a place for it. If it doesn't work, we throw it out. Seriously. All right, conformity. Conformity in math. You have to have conformity in math. If not, then what? Every single solitary math test you take, we get 100%. You agree or disagree? Yeah, depending on how you do it. Think about, no, yes, everything would be 100%. If you can prove logically why you did things, right? Everything would be 100%. You would have 27 different answers to the same problem, but everyone would be right. So take a look, this is just a quick example. We start you off very basic, and we talk about your orders of operations, right? Why do we have to have orders? Because if you did not have orders of operation, you can get all those different answers. So you have to have conformity in some cases. Right? Questions, comments? You can jump in anytime. That's all right. All right. You guys know orders of operations. I should have taught you that back in little kid school. All right. All right. Newton, science guy. He could not do the science that he wanted to with the math that was available. And this is what we're getting into. I studied calculus for the physics, but really it was Leibniz that actually had it earlier. So the question was it invented or discovered? We already covered that. Math is always discovered. It's out there. We just got to get our brains around it to figure out how it works. Now, okay, beliefs in mathematics. Come on, this is Algebra 1 stuff. What is ax plus by equal to c? Is that the equation of line in standard form? Yes or no? Yeah, everybody knows that, right? But what if I told you it's not? What if I told you that everything that you've been told is a lie? Because you can't handle the truth. That is not an equation of a line.
Then why
What
do
about
they
it?
teach it?
Y equals mx plus b.
Well, yes, we
Yeah,
can
it's just
rearrange that. Why do we teach it? Because you can't handle the truth. What are you laughing?
What is the truth?
What is the truth? That's an equation of a plane. All right. Go to my next slide.
Why is the truth limited to certain people?
Because we do not teach you about equations of a plane. Equation of a plane is ax plus by. In this case, it's 0z. 0z means z can be anything. So when you have an equation of a line, we're looking at it in 2 dimensions. Give me your pencil. Thanks. I forgot my meter stick. I can use that. All right, equation of a line, right? Well, we look at it as ax plus by is equal to c is equal in 2-dimensional world. But really, what world do we live in? 3 dimensions. There is a z factor that comes out. But when we talk about, why are you smiling? There's no smiling in my class. No, you talk to any of my other students. You want to have fun, go to a social studies class. All right?
Not with my teacher.
So, equation of a line. The z value could be anything. And we tell you that because we take it in small steps. Think about it when you first learning math. Didn't you take math? Okay, here's the 0. Everything on this side is the negatives. Everything on this side is the positives. And you mess around with 1 dimension. Then, after you got the 1 dimension kind of taken care of, what did we do? Give me your pencil. Thank you. Pen. We took in 2 dimensions. Now you're learning everything in 2 dimensions, which is your x and your y values. And as you progress farther in your math, guess what we do? We take you to 3 dimensions. As you progress farther and farther than that, guess how many dimensions you can go to? 11. Up to about 11. Sorry, what was that? Yeah. Days. Yeah. We just can't see it. It does exist. How do we know it exists? We can do mathematics in it. Right? Just because you live in a 3-dimensional world does not mean that there's not 4 dimensions or 5 dimensions. Now, think about it logically. If you live in a 2-dimensional world, all you would see is straight ahead, 2 dimensions. You cannot look up or down. Does not mean that the up and down does not exist. We just can't see it. We don't live in that world. We live in a 3-dimensional world, right? Does that mean that we do not, there isn't 4 dimensions? Yeah, there is. We can do math in it. Math tells you, yeah, guess what? Right.
What would a 4-dimensional world look like?
That's a very tough question. That's one that everybody's trying to answer. Okay? We cannot see it. Why cannot we see it? What world do you live in?
3 dimensions.
That's right. That's all we can see is 3 dimensions. Right?
So does that mean we'll never know?
So
Now-
like on a graph or like a plane, what would 4 dimensions?
You can't. I don't have my meter sticks. I should have brought different props. I don't know where this is going, but we'll work on it. Okay? All right. If you're in my class, you know where this is going. 1 dimension line, 2 dimension. These 2 lines are perpendicular to each other, right? 3 dimension, 3 lines, all 3 lines are perpendicular to each other. Okay? That gives us our x, y, and z values. Now, do the best. Okay, I don't care what he says about you. Okay? So, 4th line. We have to put this line so it's perpendicular to these 3. Go ahead.
You can't do that.
You cannot do it. We live in a 3-dimensional world. We can only see 3 dimensions. It doesn't mean that the 4th dimension does not exist. Now, let me give you, can I go off topic?
Absolutely.
Okay. I don't know who these are. Make sure to get back. Now,
If you couldn't do the 4th dimension with your little diagrams, how do you do it with math?
oh, yeah. We have to go a little bit different. Then it's ax plus by plus cz plus dx or whatever. Whatever it is, next time. Make for another variable. Because each of these are a different line. So
no, I was just
in a
kidding.
4 dimension, it could be like, I don't know, ax, let's go y. What's before x? What letter is before x? W. So we go AW, right? BX. CY plus DZ is equal to some number. That's 4-dimensional. Because those are 4 lines that we're looking at. Each one of those letters represents a line. Right? Does that make sense? Kind of? We just can't see it. It's kind of difficult to grasp your head around it. Go ahead.
Why do you say that there's only like 11 dimensions? Why?
That's people smarter than me have proved that. Okay? So we're not going to go there because I don't even think where they're thinking. Like I actually can think like up here a little bit, right? They're like above the roof of the ceiling and keep on going. That's where their minds work. That makes sense? I don't even consider myself, yeah.
That's
If I thought that way, go ahead.
Some applications in an attempt to try and get you to visualize it, which is going to be poorly done, but the idea of multiple dimensions led to multiverse theory and the idea of like what is our universe expanding into, which we talked about earlier, as well as it led to, I'm pretty sure it led to the discovery of our new concept of a model of an atom where electrons disappear
Yeah.
and then come back.
And then,
Right? That they're not transferring clouds, they're actually gone. And where they go, theoretically, is another dimension that we can't see. And that's how energy is transferred, which leads us back to stuff like string theory.
yeah, that's where everything starts coming in.
Wait. Do they know what's in the other dimension? Like, do we like have any idea of like if it's like an alternate universe to ours?
It could be. Keep on going.
That'd be so cool.
So isn't that like proof of the multiverse theory? If we know that multiple dimensions exist, and they
That's
have
what they're working on.
But like, isn't that proof? Can they
No,
exist?
not necessarily, because we can only judge our mathematics and physics of what we know in the universe that we're in. Multiverse theory basically suggests that there are universes where those physics don't have to be the same. In order to really prove that, we can't prove the multiverse theory. So we know to understand anything that is physics and mathematical calculations when it comes to physical laws of our universe, they don't hold true in other universes.
Because there's like multiple dimensions.
Right, like the constant for time or gravity in another universe would be completely.
You guys are thinking, I like that. Because reality, we live in a three-dimensional world where our three-dimensional laws apply. 4, 5, 6 dimensions, you don't know what laws apply there and how it works. You can't even see them. We can do math, we can guess, we can make a theory, but we can never prove it. All right?
So if we're in a three-dimensional world, then wouldn't the first and second dimension just be concepts to us? If they're
No, we haven't.
three-dimensional?
Because we have to have all 3 dimensions in order for it to work. Our first dimension is straight line.
Then why would we consider a fourth dimension?
Huh?
And why would we consider a fourth dimension? It's all.
It's because we're not living there. Doesn't mean it does not exist. We just can't
But if
see
we're
it.
the world, then what is outside of it? Like, is the world just Earth? Or
Wait, so I'm
Wow, look what you're thinking. All right, we're not going to go there. All right, next. Let you guys discuss it because believe it or not, I'm supposed to be teaching a class right now. What time is it?
11, we got about 9 minutes.
9 minutes. All right. All right. Some of you actually know this and keep your mouth shut. Everybody knows geometry. Geometry states, hey, guess what? The sum of the interior angles of a triangle is 180. True or false statement? True. False.
Everything I know is a lie.
Yeah, because why? Why is it a lie? Because you can't handle the truth. I can use my fries.
I can't handle it.
All right.
When my teacher tries to teach me,
Lie
I
down.
can be like, I can't handle
Bye,
it.
please.
All right, don't worry, I'm going to be done talking. You guys can leave and make fun of me later. All right. Is this a line right across here? Yes, it is. Is this a line that comes from here to the North Pole? Yeah. Is this a line that comes from here to the North Pole? Yeah. So what is the angle measure here? 90 degrees, because it intersects at 90. What's the angle measure here? 90 degrees. So I can close this up, which is a triangle, and it runs from anything greater than 180, and then I can open it all the way to here, and I can still get a triangle to how many degrees? Almost 360. So, when you're talking about the interior angle sums of a triangle, you better be talking about the triangles on a plane, because there are triangles that exist in other parts. We apply the mathematics. When I'm talking about a triangle, I'm talking about a triangle on a sphere. Triangles on a sphere have to be greater than 180, but less than 360. Because if it was 360, I would only have 2 lines, which does not make a triangle. Quit smiling. Okay. You guys ready for the next one?
Probably not.
All right, geometry. Depending on who's driving.
I can't handle the truth. We established that.
This gets you thinking, and I'm going to explain a little bit later. Okay. 2 lines perpendicular to a line is there are two lines perpendicular to the same line are parallel to each other. Agree? Yes. Right? Right? Wrong. All right? I'll explain. Parallel, well, let's scratch that. Parallel lines never meet, right? Wrong. Wrong. Sometimes they do. Hold on. Line. Longitude is perpendicular to the equator. Longitude is perpendicular to the equator. Are these two lines perpendicular to the equator? Follow them up. Where do they intersect? Okay. All right? A little louder?
They're not straight.
Yeah, they're
Oh,
not.
they are. They are straight.
Everything's straight, but that doesn't mean that
They're
they're
not on a plane.
Not on a plane. Let me explain. So, oh, here's the next one. You guys will like this. What's 5 plus 5?
Oh, no. I don't want to answer.
Not 10. Well, it could be.
Yeah.
All right. So the answer is, you guys like this. It's 0, 1, 2, 3, or 4. Sometimes. There's different mathematics out there. We only teach you what we need to teach you at the high school level. Okay. There is mathematics that deals with remainders. Who does computer science here? Computer science, anybody? We deal with remainders. Okay. So, how many times can 5 go into 10? Division. What's 10 divided by 5? 2. Right? Is there a remainder? What's the remainder? 0. Right? You guys agree with that? Depending on what remainder that I am looking for. Now that is mod, I'm going mod 5, right? So what's my number if it's mod, if my remainder is 1? I'm going 11. Right? Well, 11 is that, 3. All right. We deal with remainders. So when we say in a different modular arithmetic, depending on what we're dividing, we look at the remainders. Either it could be 0, 1, 2, 3, 4, or whatever we want it to be. All right. We deal here with the basics at the high school level. When we deal basics in geometry, we only deal with planar geometry, geometry on a plane. But there's geometry on a sphere. There's actually geometry within a circle, okay? All the geometry that takes place in a circle. And also there's projective geometry. In other words, who's an artist here? You an artist?
Not really.
Close enough?
Yes.
Sure. When you draw something in perspective, do you have a vanishing point?
Yeah.
That vanishing point is another aspect of geometry. It's called projective geometry.
Where's hyperbolic?
Hyperbolic geometry or hyperbolic function.
Geometry, where's that called?
Can I get back with you on that?
It's
Okay.
just I watched a TED talk on like how the observation of coral and crocheting coral.
See, there's hyperbolic functions, which is a hyperbola,
Yeah.
right? It might work off of that, but let me get back with you on that. All right. Okay. Something to think about, because we can only teach you so much. Why?
Because I can't handle the truth.
You really can't handle it yet. We need to get you the basics, and once you get the basics and have those wired-tight, then you apply those basics to different concepts in different places. Math in and of itself is nothing, okay? If you think about it logically, if you don't use it for something, you're not going to walk through the store and say, ooh, look, there's 5 plus 5, right? Ooh, there's a quadratic equation I got to solve. You'll never see that. You apply the math to certain problems, okay? All right, I gotta go teach another class. Actually, I'm gonna go eat my lunch. All right. I hope you enjoyed today's lecture.
If there is